Hi, I'm Keenan Crane from Carnegie Mellon University, and in this talk I'm going to take a deep dive into some recent tools for optimizing shapes based on the principle of repulsion. And these tools are not only quite new in mathematics, but they also turn out to be very natural for a wide range of problems in visual and geometric computing. So the basic problem is that we're given some geometry, a collection of points or curves or surfaces, and we'd like to find a nice, well-distributed arrangement of this geometry in space that avoids any self-intersections, possibly subject to constraints on things like length or area, or in this case, the geometry has to be confined to this bunny shape. And so we're going to talk about how to formulate this problem mathematically, how to solve it computationally, and also how that opens the door to a bunch of new applications. The work I'll discuss comes mainly from two papers, one on repulsive curves with Chris Yu and Henrik Schumacher and myself, and then one on surfaces, also with Caleb Brackenseek. Here is a high-level outline of the talk, and I know how easy it can be to shut off a video as soon as you feel lost, so I've organized the talk into levels of difficulty. If at some point you feel like giving up, well, you might still find something cool and interesting by just skipping to a later section. So first and foremost, why would we want to solve this kind of problem in the first place? Well, look, if we think about just point repulsion, this already shows up as a basic computational tool across every major area of computer graphics. For instance, in geometric modeling, well-distributed points are used to compute meshes with nice element quality. In image processing, repulsive points might be used to find nice stippling patterns. In rendering, point optimization helps to improve, for instance, the distribution of samples used for density estimation. And in physically based animation, repulsive points show up as a basic component in solvers like SPH and other point-based methods. Yet, given all the applications of point repulsion, there's surprisingly little work on algorithms for repulsive optimization of curves and surfaces. So, why might you care about higher dimensional repulsive geometry? Well, one perspective is to think about regularization. So in general, a regularizer helps to provide smooth solutions when fitting data. So for instance, you might want a function that matches your observations, but also has small derivatives. In geometric problems, curvature functionals like Euler or Willmore energy have traditionally played the role of regularizers, enabling us to fit data while keeping the fit smooth. But these classical functionals have one glaring flaw, which is that they allow geometry to pass through itself, even if the initial data was free of self-intersections. So here, a repulsive regularizer makes a whole lot of sense. Another basic reason is that the no intersection condition is quite natural when we want to draw or design things. For instance, if you click out the vertices of a non-intersecting polygon using a standard drawing tool, nothing about standard spline interpolation schemes guarantees that your interpolating curve will be free of self-intersections. Okay? Likewise, if you want to model 3D geometry that's destined for the real world, let's say you want to 3D print something, well then you'd better make sure that it doesn't pass through itself. And finally, when visualizing data, unwanted intersections can really change the meaning of what you're looking at. So for instance, if you're drawing a graph, you might be really sending the wrong message if two edges intersect, and so you might like to optimize the edge curves to avoid intersection. Mathematical visualization is another place where repulsive energies can be extremely powerful. For instance, if I want to convince you that a knot can be untangled to a circle, I might draw a diagram like this one, which is pretty hard to believe if you don't know how to read it. In contrast, if I can just make a movie of this transformation, then the proof really is in the picture. Likewise, there are all sorts of counterintuitive things that can happen with surfaces that are really hard to communicate with a drawing, but can be made into beautiful animations if we have the right tools. And we'll look at a few of those examples today. Finally, there are some very natural connections between repulsive energies from geometry and those showing up in physics and biology. In particular, electrostatics is critical to understanding and predicting and designing various physical systems. So in microbiology, long-range interactions between membranes and proteins and so forth are mitigated by the electrostatic potential from ions in a process called Debye screening. And so you really need to think about repulsive phenomena of all different dimensions, right? You have zero-dimensional particles like dust and proteins and viruses. You have one-dimensional curve-like phenomena where repulsion has a significant effect like supercoiled DNA. And you have two-dimensional phenomena, for instance, synthetic biomembranes, which might be used for water filtration or drug delivery or all sorts of other interesting things. Now, it's really important to make a clear distinction between repulsion and collision avoidance, which is also sometimes handled using potential functions. But computationally, these are very different problems. Okay, so the right mindset for collision avoidance is contact mechanics. If I shoot a cue ball, then right before the moment of contact, I have a potential that activates to avoid collision. In contrast, if all the balls on my pool table were charged particles, then I'd need to simulate a potential that's active all the time and has a long-range influence on all pairs of objects. So with these local potentials, the goal really is to try to prune away and ignore any long-range interactions, whereas with repulsive energies, it's really the long-range balance of forces that's interesting, and that's what we want to keep. Likewise, the potentials we use for contact are kind of pseudo-physical. They're kind of a numerical device used to enforce inequality constraints, whereas to get nice-looking repulsive curves and surfaces, we're going to need to really start with a smooth energy and apply a principled discretization. So with this new problem comes some new challenges. For instance, if we just try to naively apply the same energies we use for points to curves and surfaces, the energy diverges, leading to severe numerical instability and inconsistency with respect to tessellation. Minimizing these energies can be very challenging, even if we use kind of the latest and greatest preconditioners from geometric problems. Optimization can easily get stuck. And finally, we need to consider interactions between all pairs of points, which means our problem quickly blows up in size if we consider a discretized curve, or worse, a discretized surface. And this is especially hard because we're going to have to invert a large, dense matrix. Okay, so for these reasons, our approach to repulsive geometry optimization has three main ingredients. First, we introduce a discretization of the so-called tangent point energy, which is well behaved for curves and surfaces. Second, we develop an intelligent optimization strategy specifically tailored to navigating the repulsive energy landscape. And finally, we build a fast hierarchical acceleration scheme to bring down the asymptotic cost of solving our dense system. And apart from all this technical stuff, a really important component of this work has been identifying new ways of applying repulsive energies to problems in visualization and geometry processing and visual computing. So, how do we model repulsive geometry? Well, the basic idea is to define an energy E, which assigns a score to any given curve or surface. And we're going to say this energy is repulsive if it's finite when there are no intersections and infinite otherwise. So we want an infinite barrier to things running into each other. An energy that naturally comes to mind is the Coulomb potential from electrostatics, which for two particles of equal charge is inversely proportional to the distance between them. So basically, two particles want to move as far away from each other as possible. And the gradient of this energy with respect to the locations of the particles gives the force of repulsion, telling the particles where to go. Now, importantly, this energy is repulsive. As two particles approach the same location, the energy blows up to infinity. Unfortunately, although Coulomb potential makes sense for points, it's not a very good energy for curves or surfaces. So let's say we integrate the Coulomb potential over all pairs of points x and y on the curve. Then if we fix x and follow y around the curve, the integrand will look something like this. Okay, so it gets huge for points y that are immediate neighbors of x along the curve, but only goes up a little bit when the curve gets close to itself. And this is not really what we want, right? We want the energy to be biggest where the curve almost intersects so that the forces can push it apart. The fact that x has some nearby neighbors y is not really interesting. We don't want forces that are just trying to rip the curve apart. We can also plot the contributions of all pairs of points x and y simultaneously, and notice again that the near intersection is just a tiny little bump in the overall integrand. What's worse is that the Coulomb energy is not even repulsive. It can integrate to a finite value even if there's an intersection. Now, we can try to fix this by raising the integrand to some power alpha, but it turns out there's no useful value of alpha. If alpha is less than 2, the energy is not repulsive. If alpha is greater than 1, then it's infinite for all curves, including ones that don't intersect, which means the energy gradient in this case doesn't give us any useful information about how to push the curve apart. That being said, nothing stops you from plugging this energy in and trying it out anyway. But more often than not, you're going to get results that you may not like. So why does this seemingly natural idea of just repelling all pairs of vertices work so poorly? Well, basically, the effort is just focused on the wrong thing, repelling your immediate neighbors rather than preventing self-intersections. And while you can, of course, tweak parameters and add constraints and add regularization to try to make things better, you're fighting a losing battle. The underlying energy is simply not well defined. So for this reason, people have come up with other energies that work better for curves. For instance, the so-called Mobius energy sort of ignores immediate neighbors by saying, if x and y are 2 points on the curve, then we're going to penalize 1 over the Euclidean distance squared minus 1 over the geodesic distance squared. In other words, the distance in space versus the distance along the curve. If there's a near intersection, then the first term will be large and the second one will be small, and so the contribution to the energy will be big. But if the 2 points are just neighbors along the curve, then the Euclidean distance and the geodesic distance are almost the same, and we can ignore this pair. Okay. However, this energy still has a couple of drawbacks. One is that it's Mobius invariant, and in particular, it's scale invariant, which means that we can't always see tight spots where the curve is actually very, very close to itself. Another, which is going to be super important for surfaces, is that geodesic distance is expensive to compute, but also very hard to optimize. So this is still not really an ideal energy for applications in visual computing. Instead, we're going to use something called the tangent point energy, where the idea, again, is to ignore immediate neighbors, but in a way that's more friendly to computation. So for 2 points x and y, we'll let r of xy be the radius of the smallest sphere that passes through y and is tangent to the curve or surface at x. Then we'll take 1 over this radius raised to a power alpha. If the points are close in space but distant along the curve, then the sphere will be small and the energy will be large. If, on the other hand, the points are close in space and close along the curve, then the sphere will be huge and the energy will be very small. And you can also show that as long as this power alpha is greater than 2, the energy is both repulsive and, unlike the Mobius energy, it's no longer scale invariant. Okay? So it's pretty much exactly what we want for applications in visual computing. The parameter alpha, by the way, just gives some control over how local the effect of repulsion is. So as we increase alpha, we care less and less about avoiding things that are very far away. What's also nice is that the tangent point energy automatically provides some regularization of sharp corners and kinks, because as y approaches x, the tangent point radius approaches the osculating radius, which means 1 over the radius approaches the usual curvature at x. So tangent point energy also behaves like a sort of a non-local bending energy, similar to but different from an elastic rod or elastic plate. Okay, so if we integrate this quantity over all pairs of points x and y on a curve, then we get something like this. So as y goes around the curve, the energy remains small as we approach x, we ignore the immediate neighbors, and it only gets big at spots where we're close to self-intersection. Likewise, if we plot the energy for all points x and y, we can see that all of our attention is now focused on points where either we approach this self-intersection or where we start to develop sharp corners. And so the corresponding forces, in other words, the energy gradient, now provide some actually useful information about how to improve the curve and avoid self-intersections. So now we have a pretty nice energy and we need some way to actually minimize it. And this turned out to be pretty tricky. Repulsive energies are a bit different from many of the energies we're used to because, first of all, they're non-local. They involve all pairs of interactions. And second, they involve high-order fractional derivatives, which is something we don't usually encounter. And so if we just try to do naive gradient descent or some other standard scheme, we'll end up with super slow optimization that takes extremely small time steps. So our approach is to use something called Sobolev preconditioning, which in general is a powerful technique for optimization of geometric functionals. It's sort of well known among a small community of researchers, but I'd say it's still not very widespread in terms of most people realizing that, yeah, this is a very useful technique. In the past, it's been used for a number of problems in shape optimization and curvature flows. It's been used a little bit for mesh generation and more recently for problems in sort of elasticity-inspired injective mapping. But for repulsive energies, we're really going to have to do some additional work to generalize to the non-trivial case of non-local problems and fractional derivatives. So how does this work? Well, in general, if we want to minimize an energy E of F, then we might follow its gradient flow. Just make the change in F equal to minus the gradient of E at the current F. If we discretize this equation in time, we get the standard gradient descent algorithm. The new F equals the old F minus some time step tau times the gradient at the old F. Now, one extremely important fact is that there's not just one definition for the gradient. It depends on your choice of inner product. And that's going to have a huge impact on optimization. So more explicitly, the differential of an energy, E, called dE, tells us for any direction u, what is the change in E if F moves with velocity u, okay? The gradient is a different quantity whose inner product with any u gives us the differential in the direction u. So for instance, if we think about the inner product as being given by a positive definite matrix A, then the gradient is related to the differential by the inverse of A. And since there are many possible choices of inner product, that means there are many possible ways to do gradient descent. One classic example is Newton's method. So if I apply ordinary gradient descent, where the inner product is the identity and the gradient is just the differential, then I might end up zigzagging back and forth across a long, narrow valley in my energy landscape, because the steepest direction with respect to the standard inner product does not necessarily point directly to the minimizer. Newton's method, on the other hand, replaces the identity with the Hessian, resulting in a preconditioned gradient that, at least for this problem, takes us straight down to the bottom. But in general, unfortunately, Newton's method is far from perfect because it's based on a very simple hypothesis that a local quadratic fit will provide a good approximation of the global energy landscape. And away from local minima, this is just not true. Newton's method is a pretty crude heuristic. So for instance, if this is our energy landscape, then the ideal thing would be to go straight down toward the global minimum. But this is not what Newton's method does. In fact, when the Hessian isn't positive definite, it might take us to a saddle or even to a local maximum. And to make things worse, it can be really difficult and expensive to evaluate, especially for a non-local problem like ours. So we'd like a scheme with the good local convergence behavior of Newton, but that works a bit better for repulsive energies. And our alternative is to use Sobolev preconditioning, which replaces the Hessian with a Sobolev inner product. So what's a Sobolev inner product? Well, the standard L2 norm, or L2 inner product, just measures the size of the function values themselves. For instance, the inner product of u and v is just u times v integrated over the domain. Whereas a Sobolev norm is also going to capture the size of derivatives. So for instance, the H1 inner product integrates the dot product of the gradients of the two functions. Okay? There are then three ways to think about Sobolev preconditioning, which I'll talk about. One is that the Sobolev inner product sort of smooths out or blurs out the gradient so it has more of a global effect. Another is that it reduces energy in all spatial frequencies at the same rate. And a third is that it effectively cancels derivatives in the gradient flow equation, thereby eliminating a mesh-based time step restriction. Since the full-blown story takes a bit of work to explain, we're going to start with a simpler toy example of Dirichlet energy. So Dirichlet energy basically measures how smooth a given function is by integrating the squared norm of its gradient. For instance, this function has large Dirichlet energy, this one has much smaller Dirichlet energy. We can also write Dirichlet energy as the L2 norm of the gradient, or using integration by parts, it becomes the inner product of Laplace f with f itself. From here, it becomes easy to take the derivative with respect to f, telling us that the differential in the direction u is just minus the L2 inner product of Laplace f with the given direction u. Okay, so how about the energy gradient? Well, remember we said the inner product of the gradient with any function u should equal the differential in the direction u. And this time around, let's just use the standard L2 inner product. So for Dirichlet energy, we said the differential dE is minus the Laplacian of f, L2 inner product with u. And so we want to solve the equation L2 inner product of grad E with u equals L2 inner product of Laplace f with u, which must mean that the L2 gradient is just minus the Laplacian of f. If we plug this into our gradient flow, we get an optimization scheme that looks like heat flow. At each moment, the change in F equals its Laplacian. And so heat flow will slowly smooth out little bumps, gradually decreasing Dirichlet energy. Though what you notice is this one big bump in the middle still remains. So let's see if we can do better by using a Sobolev inner product. For instance, the H1 inner product. We can rewrite the left-hand side in terms of L2 by sticking in a Laplacian, okay, which tells us the Laplacian of the H1 gradient must equal the Laplacian of F. In other words, the H1 gradient is nothing more than F. So our gradient flow now just says the change in F should be proportional to F. And this works perfectly. We quickly eliminate all the bumps and reach a Dirichlet energy of 0. From here, it becomes really tempting to ask, okay, well, can we do even better? For instance, maybe we should try an even higher order Sobolev inner product like H2. So this basically just means we're going to use the square of the Laplacian rather than the Laplacian as a preconditioner. Okay, and so maybe we could call that resulting preconditioned gradient inverse heat flow. But if we run this, it doesn't work very well. Big bumps get eliminated very quickly, but small bumps now stick around for a very long time. So sort of the opposite of what happened with the L2 inner product. So the takeaway here, and really the story of all Sobolev preconditioning, is that you're usually much better off if you can match the order of the preconditioner to the order of spatial derivatives appearing in the differential. A good mental image, which we've kind of hinted at, is to visualize frequency space. So here, if I project Dirichlet energy onto a pair of low and high frequency eigenbases, then we can clearly see the L2 gradient flow gets rid of high frequencies very quickly, but has trouble eliminating low frequencies. H2 gets rid of low frequencies, but struggles with the high frequencies. And H1 reduces the energy in all frequencies at the same rate, very quickly reaching the minimizer. Okay, so again, the key idea is don't just pick an arbitrary inner product, really think about how to match it to the order of derivatives in your gradient equation. Another good mental image is that if you pick a preconditioner of the right order, then it's going to nicely smooth out the gradient over the whole domain. So you're making steady progress everywhere rather than just in the one or two spots where things are really bad. So here, if we minimize tangent point energy with respect to L2, then all the effort is focused on the points where the curve is nearly in contact with itself, indicated by these red velocity vectors, whereas the Sobolev gradient enables the whole curve to move around and reduce energy, as we see with these blue velocity vectors. Okay, but I'm jumping the gun here a little bit because I haven't actually said how to do preconditioning for the tangent point energy. So what is the ideal preconditioner in this case? Well, again, I'd like for the order of the preconditioner to match the order of the differential. But there are a couple challenges. For one thing, the energy isn't written down in terms of derivatives. It's written as an integral. So I can't just inspect this expression to figure out the right order of preconditioner. For another, as far as I know, nobody's ever written out an explicit expression for the differential of this energy, so I can't look at that either. And instead, what we had to do is infer what the differential order must be by considering the function spaces associated with the problem. And this leads us to a differential of fractional order, which ideally should be preconditioned with a fractional Sobolev inner product. Okay, so let's see how this all works. So to cover both the curve and surface case, let's first rewrite the tangent point energy for an embedded manifold of any dimension n. Then if f is a C1 embedding of M, we're going to say E of f is the integral over all pairs of points x and y of the inner product of the unit normal n at x with the difference between f at x and f at y over the distance squared, all raised to the power alpha. And as before, the numerator says that if 2 points are close together in the tangential direction, then the contribution basically gets ignored. And so also like before, this energy will be repulsive as long as alpha is greater than 2n. So 2 for curves and 4 for surfaces. A recent theorem of Blot then tells us that in order for an embedded curve or surface to have finite energy, it must be at least s times differentiable, where s equals 2 minus n over alpha. So for instance, a curve with a sharp kink in it will have infinite energy even if it doesn't intersect itself. Okay? In turn, we can argue that the differential dE must decrease the order of the embedding by 2s, where 2s will always be a fraction rather than an integer for any dimension n and any repulsive power alpha. Okay, so in short, even if you didn't follow any of that, the point is that unlike most energies that you encounter in geometry processing or computational mechanics, the derivatives of a repulsive energy effectively have fractional order. What does that even mean? What is a fractional derivative? Well, there are several ways to understand fractional derivatives, but the intuition is they sort of interpolate between ordinary integer order derivatives. For instance, if we have a function f like this, whose second derivative looks like this, then we get a continuous family of lower order fractional derivatives going all the way back to the original function. More formally, the sort of differential viewpoint is that you take a standard differential operator like the Laplacian and raise it to a fractional power. So explicitly, you could do this with a spectral expansion where phi I are the eigenfunctions and lambda I are the eigenvalues. And then to apply a fractional Laplacian, you just raise each eigenvalue to a fractional power. The integral viewpoint is that the fractional Laplacian can be expressed in terms of an integral that looks a bit like a repulsive energy. So integrate over all pairs of points in Rn the product of the difference of the functions at x and y divided by the distance raised to a fractional power. Okay, so just like we use the Laplacian delta to define ordinary Sobolev inner products, we can use the fractional Laplacian delta sigma to define a fractional Sobolev inner product. So we get, for instance, the H sigma inner product for any real positive sigma by just inserting delta sigma into the L2 inner product. Okay? But with one little gotcha, which is that in our case, we need to consider functions on a curve or a surface rather than all of Rn. So one idea is to build a fractional version of the curved manifold Laplacian, in other words, the Laplace-Beltrami operator. But unfortunately, a full spectral decomposition is way too slow. And we also don't have a nice integral expression that works on curved domains. So what we do instead is replace the intrinsic distance with the extrinsic distance in this integral expression. And we also tack on some additional integer order derivatives d to match the desired order of the differential. And so the overall operator a sub sigma is now our fractional inner product up to some low order terms that I won't discuss here, but are discussed in the paper. Okay, so to recap, the idea of Sobolev gradient descent is to precondition the differential using an inner product of the same order as the differential. The differential of the tangent point energy has fractional order 2s, so we construct a fractional Sobolev inner product of the same order. Our final optimization strategy then looks the same as before. We precondition the differential using our fractional inner product, and we use this fractional gradient to perform gradient descent. Now, just as in our toy example, optimization works best when we use a preconditioner of the right order. So for instance, let's say we want to minimize tangent point energy for this curve, which should untangle into the round circle. If we just use L2, then we're going to make very slow progress. If we use H1, things improve, but we still don't quickly reach a minimizer. If we use H2, we now focus a bit too much on large-scale features and don't smooth out sharp corners. And finally, if we use our fractional inner product, we get to the minimizer and we get there extremely quickly. So it really makes a big difference in practice to get the order of preconditioner right. Here's an analogous example for surfaces where we try out these different preconditioners on a mesh of various resolutions going from top to bottom. So the tangent point energy in this case should turn this bumpy mug into a round torus. And what we see is that as the edge length decreases, most of the preconditioners make less progress because they have to take smaller steps. Except for our fractional preconditioner, which gets to the minimizer in roughly the same number of steps. We've effectively eliminated this mesh-based time step restriction. So this is really the payoff. If we can construct a preconditioner whose order perfectly matches the derivative of the energy, then optimization becomes asymptotically faster than other preconditioners, which means even if there are very different per step costs, the optimal order scheme will always win out as the mesh gets finer. Of course, our goal is going to be to make the per step cost very small, which we'll do in just a minute. But first, to do any kind of computation or optimization, we need to discretize our energy. And here we adopt a very simple discretization. Curves become polylines, surfaces become triangle meshes, and we approximate the energy with low-order quadrature for each element pair. Now, we could use higher-order spline bases, but since we can't exactly integrate the energy, this is really just a choice of fewer elements and more quadrature points versus more elements and fewer quadrature points. And our preference was to keep all the formulas as simple as possible. For surfaces, we also found it was very important to remesh the surface during optimization to avoid getting stuck. And of course, as a precondition, we assume that the input is already free of self-intersections. More precisely, for a curve, we're going to write the tangent point energy as a piecewise integral over all pairs of edges I and j of the usual tangent point kernel k. Now, since a polygonal curve has sharp kinks, we have to ignore neighboring edge pairs because otherwise we'll always get infinite energy. But this is an okay thing to do since, unlike Coulomb energy, the tangent point energy doesn't blow up along the diagonal. And so as we refine the curve, we're emitting a negligible contribution to the overall energy. In particular, we apply the trapezoid rule to each integral, giving us a sum over pairs of distinct edges of the tangent point kernel evaluated at all four pairs of endpoints using the edge tangent ti times the two edge lengths li and lj. For surfaces, it's not much different. We sum over pairs of distinct triangles S and T, the two triangle areas AS and AT times the magnitude of the inner product of the unit normal at S with the difference between the triangle barycenters XS and XT divided by the square distance between barycenters, all raised to the power P. We can check the rate of convergence by comparing to the tangent point energy of a known smooth surface. And interestingly enough, even though we use linear elements, we get a convergence rate that's closer to quadratic with respect to the edge length h. To get the energy differential, we just take partial derivatives of the discrete energy, and to precondition the differential, we also have to discretize the fractional inner product. Our strategy here is very similar to what we did for the energy. We just use low-order quadrature, summing over pairs of elements, and omitting immediate neighbors. Importantly, the final inner product is a dense matrix, and so in a few minutes, we'll talk about how we can invert this matrix efficiently. Finally, I mentioned that for surfaces, remeshing is very important because large deformations can lead to bad elements, which give a poor approximation of the energy, which can cause optimization to get stuck. So for instance, we might like to untangle a surface like this one, but without remeshing, optimization gets stuck here. And so we apply a little local remeshing at each step, where we split long edges, collapse short edges, flip non-Delaunay edges, and then apply a little tangential smoothing using the optimal Delaunay scheme described by Chen and Holst, which basically moves each vertex toward the area-weighted average of neighboring circumcenters. So on a static mesh, that looks like this. So elements gradually improve. And if we apply it during our flow, we will get all the way to a minimizer. To do interesting stuff with repulsive curves and surfaces, we also have to be able to handle various constraints, because without any constraints, the behavior can be pretty uninteresting. For instance, point charges might just fly off to infinity, or a curve grows without bound, and so forth. So we incorporate a generic constraint function, phi of f equals 0, that can describe constraints on points or edge lengths or tangents or whatever, and apply a standard projected gradient technique where we first project the gradient onto a feasible direction, and then we project the geometry itself onto the constraint set. By the way, this all becomes a bit more complicated when we want to accelerate computation, so I'll just describe the simpler unaccelerated version here. Here are just a few examples of the kind of constraints we might like to enforce. So like fixing the length of an edge or the total length of the curve, or fixing a point in space, or prescribing a tangent vector, or keeping a curve on an implicit surface, and so on. The point is you can define whatever constraint function you want. So in particular, if we let g be the unconstrained descent direction given by our fractional preconditioner, and c is the Jacobian matrix of our constraint function, then we want to find the closest direction g tilde that preserves all of the constraints, or is tangent to the constraint set. And importantly, closest here means closest with respect to our fractional Sobolev norm. So this is a convex quadratic problem that amounts to just solving a linear saddle point problem. Now, if we start at the old curve and take a step in the projected gradient direction, then we get an initial guess for our new curve that still isn't quite on our constraint set. So what we do is look for the smallest offset x that approximately eliminates the constraint violation, and move in this direction to get our new curve. This is basically a slight modification of Newton's method that again involves solving a linear saddle point problem. And if we want to do better, we can just repeat this procedure, but usually just need to run it once or twice per optimization step. Okay, so the final question is how to reduce the overall computational cost of each optimization step. So preconditioning already helps us take big steps, which is a very good thing, but the per step cost can still be quite high. For instance, in 3D, if h is the average edge length and n is 1 over h, then evaluating the energy or its differential is already an order n to the fourth operation. And what's worse is we have to build and invert a dense n squared by n squared linear system. So we accelerate computation in 3 different ways. First, we do a hierarchical approximation of our energy and derivative evaluation. Second, we use a so-called block cluster matrix to perform matrix vector multiplication. And third, we use either a geometric multigrid scheme for curves or a special decomposition of the fractional inner product for surfaces. So how do we evaluate the energy and its derivatives more efficiently? Well, naively, we'd have to iterate over all pairs of mesh elements. But we can make things a lot faster by treating clusters of distant elements as kind of one big element. In particular, we apply the Barnes-Hutt algorithm, which first builds a bounding volume hierarchy, or BVH. And we'll say a BVH node I is admissible relative to a mesh element S if it gives a good enough approximation of the total energy of all elements within I, as determined by a Taylor series analysis. In particular, we ask that the maximum bounding radius of either the element S or the node I is less than some error tolerance theta times the distance between S and the convex hull of I. The approximate energy for element S is then the sum over all admissible nodes that have no admissible ancestors. In particular, we sum up the area of S times the total area inside node I times the tangent point kernel K applied to the centers of mass and the normal of S. Using the same test as before, we can check that this scheme indeed provides a very good approximation of the naive sum over all pairs, and a nearly identical scheme can be used to approximate the energy derivatives. Next, we have to efficiently precondition the differential, which involves inverting a large, dense matrix. And our approach here is to use a hierarchical decomposition of the matrix into rank 1 blocks. So we imagine that each BVH node A corresponds to a subset of matrix rows or columns, and say that 2 nodes A and B are well separated if their rank 1 block provides a good enough approximation of the original matrix. So this is very similar to our Barnes-Hutt admissibility condition. The matrix is then partitioned into the coarsest collection of well-separated blocks, and we use the fast multipole algorithm to perform a matrix vector multiply. So now we can multiply this matrix efficiently, but we still need to solve our linear system. So for curves, this is pretty easy to do using geometric multigrid. We build a hierarchy of curves by just averaging every other node, and then use our fast block matrix vector multiply to implement multigrid. In reality, there's some additional complexity here for dealing with constraints, which I'll defer to the paper. In the end, when we put this all together, we get the desired behavior. The compute time scales almost linearly in the number of vertices and is faster in an absolute sense past about 1,000 vertices. Now, for surfaces, building a multi-resolution mesh hierarchy is a lot harder and more expensive than it was for curves, especially because we're remeshing the surface every time step. So here we're going to take a different route and decompose our fractional operator delta S into 2 integer Laplacians delta and a lower order fractional part delta to the S minus 2. Now, if we want to invert this operator, we just need to do 2 sparse linear solves using the ordinary cotan Laplace matrix, plus forward evaluation of the fractional operator, which we can do using our fast hierarchical scheme. So no multi-resolution mesh hierarchy is needed. As it turns out, this scheme is a bit too approximate to precondition the differential directly, but still provides an excellent preconditioner for an iterative linear solver like GMRes. And most importantly, if we run this scheme on larger and larger meshes, we get performance scaling that looks about as good as multigrid, except that, again, we didn't need to actually construct a mesh hierarchy. Okay, so with everything in place, let's see how well our optimization scheme does compared to other possible strategies. Our basic benchmark is to untangle some complicated curve or surface. So basically, we want to find the minimum energy configuration without ever letting the geometry pass through itself. Since there's not a whole lot of past work on this problem, we generated our own benchmark dataset of several hundred curves by randomly perturbing a bunch of different knots into very tangled configurations. If you think you can do better at untangling these knots, please go ahead and give it a try. We'd love to see that. But be warned that some of these knots are much, much harder to untangle than others. So even if you succeed on one of them, you really should try the rest of the data set. So we first tried out some classic algorithms for knot untangling from the mathematical community, like knot plot and shrink on no overlaps, and found that these methods can take forever to make progress, basically because they're not applying any kind of intelligent preconditioning. This is sort of like just doing L2 gradient descent. We also tried out several integer Sobolev preconditioners, as well as some general purpose strategies like LBFGS, nonlinear conjugate gradient, and stochastic gradient descent, and found that our fractional Sobolev method does a much better job of reaching a minimizer. That's what's shown in the middle here. And that's true given the exact same amount of real compute time. We added to this set of methods some more recent optimization strategies from geometry processing and tried untangling the entire benchmark dataset. And what we found is that the fractional Sobolev scheme is not only more efficient, whether you consider the number of iterations or the actual wall clock compute time, but also succeeds on a much, much larger fraction of examples. So even some of the state-of-the-art methods would tend to get stuck in an almost intersecting configuration, whereas we succeeded on untangling nearly all of the examples. For surface untangling, very little work had been done on algorithms before our work on tangent point energy. The one exception is the so-called cosine energy of Kussner and Sullivan, which has a similar flavor to tangent point energy and was implemented in the surface evolver package of Ken Bracke. But when we actually try this out, we find that it makes extremely slow progress and gets stuck almost immediately. So probably nobody has ever made movies of surface untangling before now. And although there are some comments that, well, maybe you just need to run it on a faster computer, we know now that's not really the story. If you want to optimize repulsive energies on surfaces, you really have to think more deeply about the mathematics. You can't just throw more compute power at the problem. Finally, we also tried out more modern optimization strategies for minimizing tangent point energy on surfaces, and again found that our fractional Sobolev scheme is much, much faster than the alternatives. And just to be fair, we also checked that that's true even if we disable remeshing, so that schemes like LBFGS can keep using the same update vectors. The most exciting part, of course, is to think about what we might be able to do now that we have fast, reliable algorithms for repulsive optimization. And here, the main limitation, honestly, is just our own creativity. So hopefully these examples will inspire some of you listening to this talk to think of new and interesting things that can be done with this technology. Just one fun animation example is untangling a pair of headphones. Of course, many of us have been frustrated trying to do this ourselves, and wouldn't it be wonderful to get a little robot to do this for us or something? Okay. Another interesting question is how to best pack longer and longer curves into a finite volume. So at some point, the curvature of this curve has to increase, just like DNA coiling up into a cell nucleus, or, okay, maybe ramen noodles coiling up into a package. If we constrain our growing curve to a surface, we again get these sort of Hilbert-like curve patterns, but can generalize these patterns now to different geometries or different numbers of curves, which could be useful for something like milling or toolpath planning. Taking this a step further, we could ask curves to align to a given vector or direction field on a surface, which again might be useful for toolpath planning or just for nice vector field visualization. Also in data visualization, graphs are often drawn by minimizing energies involving the graph nodes, the points, but of course the edge curves are just as important for clearly communicating and laying out information. For instance, a standard package like GraphViz sometimes generates drawings where edges intersect, which could send the wrong message about connectivity. So if we instead treat the edges as repulsive curves, we can get some very nice graph layouts where both edges and vertices are uniformly distributed in space. Likewise, if we have non-planar graphs, we can find nice embeddings in 3D where there's maybe less confusion about how edges get connected to vertices. Standard vector graphics tools like Inkscape or Adobe Illustrator have no knowledge of whether curves cross each other or how far they are from collision, which means if you click out some control vertices, the interpolating curve may very well intersect itself. You can, of course, imagine building vector graphics tools on top of repulsive curves that avoid any unwanted intersections, which is especially important if you're designing something like a stencil or a cutout. There's recently been interested in sort of biomimetic design. For instance, if you want to build artificial tissue, you need some way of delivering nutrients to that tissue, maybe using a network of artificial capillary vessels. And so if you'd like each point to be close to a nutrient source, well, that's something that we can optimize directly using a repulsive energy. Likewise, people are interested in designing and simulating artificial muscles of various sorts, but the algorithms for muscle fiber design can be pretty simplistic, maybe trace out the gradient curves of a harmonic function. If, on the other hand, you look at real artificial muscles, it turns out that twisting is important for getting strong forces and torques, which can't be captured by a gradient field. So instead, what we could do is constrain the endpoints of the muscle fibers to sit on surfaces representing the joints, and then use repulsive energy to optimize whatever kind of twisted arrangement of curves you like. A very different kind of application is path planning. So suppose you have these 4 agents or robots that want to travel to the opposite corner of this room. If they all act independently, they may collide or at least get too close for comfort. But if we think of the trajectories as now curves in space-time, then we can minimize repulsive energy to get new trajectories that perform this sort of beautiful ballet where agents not only avoid collision, but stay as far away from collision as possible at all times. And that's super important, especially if you have uncertainty in measurements about where things really are. Note that this is very different from doing collision detection and response, where things would just bounce off each other at the moment of contact. A whole other class of applications is mathematical visualization. So one basic question you could ask is, given a topological space like a surface of genus G, what is the sort of simplest or most ideal way to draw this shape in space? So if we minimize tangent point energy, then for genus 3, we get something with tetrahedral symmetry, like this. For genus 5, we get something with the symmetry of a cube, like this. And then for genus 11, okay, if we let it run for just a bit, then eventually we get something with the symmetry of a dodecahedron. So about as perfect as you could expect, and also giving us some sense that we're actually maybe finding global minimizers of this energy. If, on the other hand, we minimize a classic energy like Willmore energy, we'll get surfaces that aren't nearly as nice and symmetric. And that's basically because Willmore energy considers symmetry in the 3-sphere, S3, rather than in Euclidean 3-space. Of course, unless we're making sculpture, mathematical illustrations are going to be projected onto a screen or onto the page, and so we might want something that's easier to understand in a 2D projection. So here we can add a penalty that encourages the surface to be in a 2D plane, giving us these very nice kind of button-like embeddings. Or we could add another plane if we really want a linear arrangement of handles. Now, where this gets really interesting and takes us way beyond classical things like the Willmore energy is when we have knotted surfaces, meaning surfaces that are not in the same isotopy class as just a linear arrangement of handles. So in the past, the best people could do is to draw these things as sort of knot diagrams or graph diagrams. And now we can use repulsive energy to draw for the first time what these knotted surfaces really look like. So here, for instance, I'm showing all the knotted surfaces of genus 2 up to 6 crossings. And here's just a little zoom in of what one of those looks like. Beyond static drawings, it's often helpful to illustrate the transformation of one surface into another to show that something is possible or impossible. So for instance, let's say I have this linked and unlinked pair of handcuffs. Do you think I could turn one of these into the other without breaking the loops apart or letting the surface pass through itself or something like that? Well, people have tried to make nice drawings of this phenomenon, some that are very, very beautiful, but they can be really difficult to follow unless you already have a very strong geometric imagination. But if we use our repulsive optimization, we can actually make a nice continuous movie of this transformation, leaving no doubt that it really is possible to unlink the handcuffs. Okay, here's a slightly harder example. Now, if I want to remove one of these loops from around this pole, do you think that's possible? Well, okay, here are some drawings. But if you're not convinced by the drawings, here's how we can make that happen. Okay, and the thing to emphasize here is that we're not keyframing animation. There's not an artist sitting down and telling the surface where to go. We're really discovering this transformation or discovering this fact about this surface by doing nothing more than minimizing the tangent point energy. Another fun example is turning the punctured torus inside out. So I want a continuous intersection-free motion that makes the red side blue and the blue side red. And the neat trick here is to minimize the signed volume enclosed by the surface. So when this goes to 0, we get a symmetrical mid-surface, and then we can just apply a symmetry and play the movie backwards. Okay. And there we go. Finally, you can imagine all sorts of ways to apply repulsive optimization to geometric modeling and geometry processing, not only making geometry aware of collisions, which is something people have looked at in the past, but really making geometry adapt to more distant interactions. So for instance, bending these bars long before they run into each other, or making these letters grow around each other, which won't happen if you use some classic energy like Wilmore. A basic geometry processing task is to reconstruct a surface from measured data. So one of many approaches is to sort of shrink wrap a surface around the data. And this is nice for a number of reasons. For one thing, you're guaranteed to get the right topology if you know it ahead of time. It's helpful if you want to fit data to a common template. And unlike many popular reconstruction methods, you don't need consistent orientation for your points or polygons. A downside is that surfaces can get badly tangled while shrink wrapping. But this is something we can easily avoid if we use a repulsive energy as a regularizer while reducing the volume, as we do here for points or for some polygon soup. Similarly, if we shrink wrap a sequence of progressively coarser meshes, then we generate a collection of nested cages in the spirit of Sacht et al., which can be useful for all sorts of things like collision detection and multi-resolution simulation. And we can also use tangent point energy to automatically generate surface geometry with interesting detail. So much like we did for curves, we can increase the area of a repulsive surface while forcing it to remain inside a small volume to get wrinkles or to grow something that looks like nice cobblestones. Finally, though I didn't really talk about boundary conditions much, we can at least handle simple Dirichlet boundary conditions where we pin vertices to locations in space. So here, for instance, we use tangent point energy to regularize standard minimal surfaces. In other words, we minimize area, but also prevent self-intersection, which gets rid of classic pinch-off behavior and also lets us construct minimal surfaces with obstacles like this pink cube. Okay, so to wrap things up, it's worth noting that there are certainly limitations to our approach. For one, there's no way to remove the bending regularization that's implicit in the tangent point energy. So if you want to have sharp creases or kinks, you might have to think a little bit harder about how to do this. Since we approximate our energy using a finite set of quadrature points, there's no hard guarantee at the numerical level that intersections won't occur. So if the mesh is super coarse like this one, then triangles could pass through each other. Of course, here we could also use standard techniques like continuous collision detection, or maybe try to minimize an upper bound on the exact energy. There are a lot more opportunities for acceleration, like parallelization and adaptive meshing, maybe doing multi-resolution on surfaces and so forth. More broadly, there are so many questions that we'd like to answer. For instance, how do you interpolate between two shapes in a collision-avoiding way rather than just minimizing energy? How might you incorporate an elastic shell energy to retain more memory of the original shape? And so on and so forth. So in general, this is a very new topic for visual computing with lots of questions to still explore along many different axes. And so I hope I've inspired you to think about some of those questions. Thank you very much.